Okay. So far in this class, we have been studying single objective optimization problems, or, like a particular single objective optimization problem, which is that, we've been interacting in this potentially complicated sequential environment, but there was only one thing we wanted. We were measuring success based on a single criterion, which was this thing we called regret. So what if there's like two things we want, or three things, or four things? And so what I want to do in sort of the next segment of the course is generalize us beyond this sort of single objective problem, minimize regret marginally, do as well as the best fixed action in hindsight, to be able to think about multi-objective problems. Maybe there's more than one thing we care about minimizing simultaneously. Okay, so there will be a bunch of examples of these kinds of problems that we'll see, but like maybe just to contextualize this in the kind of regret setting we've been thinking about, you can imagine all sorts of natural multi-objective regret kinds of problems. That is, why is it enough to do as well as the best single expert in hindsight in a dynamic environment where, who the best expert is might be changing over time, right? Maybe, over the course of 10 seasons in, baseball, who the best team is changes over time, right? Like if you're betting on baseball teams, say, you might want to do as well as some moving window average. And so one example, this will turn out to be like an extremely simple example given the kinds of things we'll be able to do. But like one example of the kind of like multi-objective regret problem you might want to solve is you might want to say, okay, well, not just am I doing as well as the best single expert in hindsight, but actually like on any subinterval, right? Fix any beginning point and ending point. I want to be able to guarantee simultaneously for all of those subintervals that my performance on that subinterval is competitive with the best expert in hindsight on that subinterval, right? If there's t time steps in total, that's like, t squared different objectives, right? I pick two endpoints, I have t choices for each one, and that gives me a goal. I want to do as well as the best expert in hindsight on that subinterval. Okay, so now I have not just one objective, but polynomially many of them. Okay, we talked about these sort of online shortest paths kinds of problems. These are sort of like routing problems, but maybe I want to be able to do as well, not just as the best path in hindsight, but I want to be able to take into account contextual information. Like maybe I want to be able to do as well as the best path in hindsight overall, sure, but like also on, weekdays, also on weekends, also on rainy days, also the night after a Phillies game, also, whenever the best route involves toll roads, things like that. I might have many different objectives that I simultaneously want to satisfy. Maybe I want guarantees that depend on the action that I take. Maybe I want to say, okay, well, not only do I do as well as the best action in hindsight, but on those days when I decided to play action 5, I want to guarantee that action 5 was actually a good thing to play on that subset of days, right? Like it could be that I'm doing as well as the best action in hindsight, but nevertheless, I can sort of identify a small collection of actions that were just stupid for me to play. Like maybe I'm doing as well on average as the best action in hindsight, but like whenever I played action 5, that was, clearly a terrible idea. So maybe I want to do as well as the best action in hindsight, not just overall, but on the subsequence of days for which I played action 1, on the subsequence of days for which I played action 2, and so on. Okay, and we'll eventually see examples of multi-objective optimization problems that have nothing to do with regret, right? Like maybe I want to learn a hypothesis that does well predicting not just on a single distribution, but simultaneously on k different distributions. So I have an objective that says that, I want to minimize my empirical risk, not just in one place, but simultaneously in k places. That's a different kind of multi-objective optimization problem that we'll also be able to think. Okay, so that's sort of going to be the goal for the next few classes, thinking about how to formulate multi-objective optimization problems and how to think about using actually the tools we've already developed, which are really good at optimizing, this one objective, regret, to sort of, bootstrap ourselves to be in a position to solve these multi-objective problems. And probably next class, we'll start thinking about general tools for solving multi-objective optimization problems. What I want to do today is dive a little bit into a game theoretic motivation for solving these, which is computing correlated equilibria in games. Okay, so we'll talk about correlated equilibria. We'll discuss how correlated equilibria can sort of be thought of as, in a k-action game, something that comes from optimizing k objectives simultaneously. We'll formulate them in terms of a fancier kind of regret that we'll call swap regret, and then we'll set ourselves up to be able to give algorithms that minimize this kind of regret as a special case of a much more powerful multi-objective framework. Okay, so that's the plan for today. Okay. So we've studied games before in this class, or at least a particular special case, two-player zero-sum games. And so the first thing I want to do is sort of define a more general class of games that sort of shed a lot of the restrictions that zero-sum games have. First of all, there's going to be n players, and they're all going to have their own possibly different objective functions. Okay, in a zero-sum game, there was just this one objective function that one player wanted to maximize, the other player wanted to minimize. That was what was sort of encoding the fact that this was a strictly adversarial game. But in general games, not everyone's a strict adversary. There are opportunities for coordination and cooperation. It might be that, we can team up, and what's good for me might also be good for you. And so the sort of more general framework in which you can model strategic interactions is called, well, a general sum game, or just a game. And it's defined by first, a finite set of n players we'll just index them 1 through n. Second, for each player I, a closed and bounded action set. Okay, we'll also think of this maybe as a subset of some finite dimensional Euclidean space. Okay, and just sort of remembering back to when we defined zero-sum games, so far I'm defining things very generally. I haven't required that the action set be convex yet, for example. We will need that when we start talking about nice properties we might want these games to have. But at the moment, specifying that the action set is closed and bounded is just sort of a minimal requirement so that it makes sense to talk about best responses, right? Like in general, in a game, when we start thinking about what should I do given what you are doing, that's a question of how should I maximize my utility or minimize my cost. So we're solving some minimization or maximization problem over our action set. And if our action set is closed and bounded, at least that's like a well-defined thing. Okay, and then finally, for each player, a bounded cost function that I'll write as CI. And what does it take as input? Well, it takes as input an action for each of the n players. And it outputs some number, let's say a number between 0 and b. Okay, and I'm defining these things as cost functions. So like implicitly, when I use this language, the players would like to act so as to minimize their cost. Sometimes we talk about utility functions. That's just the negative of a cost function. When we talk about a game with a utility function, implicitly, the players would like to maximize their utility, but equivalently, they want to minimize their cost. Okay, so the main difference between a zero-sum game and a general sum game is now, well, there's n players, not 2, but more importantly, there's n different cost functions rather than just one. Okay, it's not that one of the players wants to minimize something and the other one wants to maximize something. These functions can be arbitrary. Multiple players could have cost functions that are entirely aligned, for example. Okay, so these are not necessarily adversarial games. Okay. Maybe just sort of a modeling note while we're on the subject of convexity. Pretty soon I'm going to start asking that actually these games have convex action spaces. And so just like in zero-sum games, you can ask, well, like, when is that reasonable? Well, like traditionally, if you've taken like a game theory class or something, probably you've seen games introduced where each player has like a finite number of arbitrary actions. Okay. Finite set is not convex, but the way that the technical condition of convexity is typically satisfied is that you say players are allowed to randomize. Okay, if my actions are I can, wear a t-shirt or a winter coat or an umbrella, I'm allowed to flip coins, and I'm allowed to make those choices with probabilistic weights, which in terms of interpretation, it means I can randomize, but in terms of the technical effect of that assumption, what it's doing is it is specifying that my action set is actually the convex hull of my finite actions, my finite set of actions. It is the probability simplex over my actions, which is just the convex hull. Okay, so allowing players to randomize, what that's doing is it's convexifying their action set. Okay. Now, because this is a much more general framework than zero-sum game, the main structural fact that we proved about zero-sum games, the minimax theorem, it's just not true anymore. Okay, so things like order of play matter, different rational outcomes can have different payoffs for different players. They're not all payoff equivalent anymore. Okay. And if you sort of remember, one of the corollaries of the minimax theorem was that in a zero-sum game, if I'm playing a minimax strategy and you're playing a maximin strategy, that jointly those two objects form what we call the Nash equilibrium. That simultaneously I am best responding to your action and you are best responding to my action. And one nice thing about the minimax theorem is it sort of meant that the computational problem of finding a Nash equilibrium was simple. Okay, both computationally and sort of conceptually. Conceptually, because I didn't have to sort of reason about what you would do given what I would do, given what you would do, given what I would do. I didn't have to think about a simultaneous move game. It was sort of sufficient to think about a commitment game where I went first and you best responded, which is something we could think about sort of as 2 steps of backwards induction. So conceptually, it was easy. Computationally, it was easy because we gave algorithms for computing minimax strategies. So general sum games are also not going to have that nice property. Nash equilibria will be something that we can still define, but there's very little we're going to be able to say about them computationally. Okay, but it still makes sense to to define and to, in principle, think about Nash equilibria in general sum games. So we'll say that a set of actions A, which is a vector of n actions, one for each player. It lives in the space equal to the Cartesian product of A1 through AN. We'll say such a vector is a Nash equilibrium if for every player I, when I look at the cost that player I suffers at this action profile, right? This is A specifies an action for each of the n players, so it's something we can plug into a cost vector, which also, plug into a cost function, which requires being told what action each of the n players is playing. A is a Nash equilibrium if simultaneously for every player, the cost that they are experiencing at that action profile is at most the cost they would have experienced had they best responded to what everyone else was doing. So it's at most the minimum cost that player I could get if, given knowledge of what everyone else was doing, she was able to best respond with the cost that minimized her action, where we're sort of using a piece of notation that's standard in the game theory literature, but otherwise maybe like a little bit weird, which is that when I write A minus I sort of mean the vector of n actions specified by A, in which I've zeroed out player I's action. And when I write AI prime A minus I mean the vector of n actions in which I've replaced player I's missing action in A minus I with AI prime. Okay, so it's the vector A1 through AI minus 1. In place of AI, I have AI prime, but everything else is as it is in AI. Okay, so it's just saying, Nash equilibrium is a game state where somehow simultaneously every single player is playing a best response to what everyone else is doing. Okay, so if and maybe you can think about this again as sort of if it's helpful, a statement about order of play. It should be that if everybody else went first and told you that they were, and told you what they were going to do. So if all n minus 1 of your opponents told you what they were going to do, then the thing you should want to do is exactly the thing you are doing in the Nash equilibrium. Okay, except that should be true of all of them as well. It should be true of everybody. So it's not actually something we can arrange by sequencing play so that different people move first. It's somehow just like a fixed point. Somehow things, like maybe it's not even obvious that Nash equilibria are objects that we should expect to exist, right? Somehow a vector of play such that things have worked out correctly for everyone somehow, that everyone is somehow simultaneously best responding to what everyone else is doing. Okay, is the definition clear? Okay. So Nash equilibrium is somehow, it's not exactly telling a story about how you might get there, but you should think of it as a specification for what stable play in a dynamic environment might look like. In that, if you somehow found yourself in a Nash equilibrium, then maybe you should expect to stay there. because nobody would have any incentive to change what they were doing, right? Like if you think about, maybe like some environment where periodically people get to reconsider the action they're playing and change that action, that if you weren't at a Nash equilibrium, then maybe you're at a transitory state because there's some player who's currently not playing a best response. They might regret not having played some other action. And so if they get the opportunity to change their action, they will. But if you're at a Nash equilibrium, nobody has any incentive to change what they're doing. So even if people periodically get the opportunity to change their action, they won't. Okay, so it's nothing about how you might get there, but at least, maybe it's plausible that if you got there, you'd stay there. Okay. So here's a theorem about existence that I'm going to state but not prove because it's sort of not on the critical path of things I want to teach you. But it is, probably like useful to know in some generality when these things exist. Okay. So here's the theorem. Fix a game in which the action sets AI are convex and closed. And the cost functions CI, which remember are functions both of player I's action and of the actions of player I's opponents, satisfy the following two properties. Okay, so they should be continuous in all n arguments. Okay, so if any player changes their action by just a little bit, the cost shouldn't discontinuously change, right? Sort of some epsilon delta kind of definition here. For every player at every action profile, if they wiggle around what their action is by just a little bit, the cost will change by only a little bit. And beyond that, if the cost function is convex in player I's action. Okay, so the cost function for player I depends on player I's, there's n arguments to this thing, but the argument for player I is special. There's player I's action, and then there's the action of all of the n-1 players. If the cost function, okay, it has to be continuous in all n of the arguments, and convex just in the ith argument, convex in the action of player I, then a Nash equilibrium exists. Okay, so this is maybe a generalization of Nash's theorem, which probably many of you have seen before. Nash's theorem is about games that have finite action sets, and what players can do is they can randomize over them. So the action sets are sort of simplices over a finite number of points. And the utility function is the expected utility when people randomize, which means it's linear. Okay, so those utility functions are linear in all of their arguments because the arguments are probability distributions over which we take expectations. And so for free, we get continuity and convexity in argument I. In fact, we get linearity in argument I. But more generally, you don't need to assume that. It's enough that you have continuity and convexity in the ith argument. Okay, so this is some non-constructive fixed point argument. But, like it should comfort you to know that Nash equilibria exist. Yes? Yeah. Yeah, so let's see. I'm gonna um, say only informal things. So interpret what I'm saying as vibes, although like I learned this word from Natalie years ago. Um, but but um, but I think there's something formal underlying this. Um, so okay, so minimax arguments, these are sort of equivalent to online convex optimization, and a lot of what we're going to talk about in this class, including what I'm going to talk about directly next, will be things that are equivalent in some sense to minimax arguments. And things that follow from minimax arguments tend to be computationally efficient. We have constructive versions of the minimax theorem that's sort of what multiplicative weights is, what online gradient descent is. Things like Nash equilibria, like these are sort of equivalent to fixed point theorems, to sort of arbitrary fixed point theorems. And we have good reason to believe that fixed point theorems are not in general constructive in any computationally efficient way. But like we sort of believe that if you give me an arbitrary game, finding a Nash equilibrium is something that I cannot in general do in polynomial time. Even if you ignore computation, we sort of have reason to believe it's something that you cannot in general do without lots of communication. You can't do it with decentralized dynamics of the sort, like things like simulating play of a game with multiplicative weights, the way we can with sort of minimax equilibria, the kinds of things we see in zero-sum games. So sort of there is sort of a underlying equivalence to something else here, but it's not to something nice like convex optimization. It's to sort of fixed point theorems. And so, like if you can prove that some problem is equivalent to finding a Nash equilibrium in an arbitrary game, that's sort of one way to provide evidence that the problem you just described is hard in the same way that an NP completeness reduction is hard. So there is a whole sort of complexity theory of Nash equilibria that sort of tries to understand what problems it is equivalent to, but the answer is that the problems it's equivalent to are hard. Good question. Other questions? Yeah, I don't have any intuition to share with you because I looked up this theorem, but I didn't read its proof, so I don't really know how it's proved. But I do cite the paper in the notes. Yeah, this was sort of among the more general minimax theorems that I could find out there. Good question. Other questions? Okay. Okay, so because of this computational intractability that we've sort of been hinting at, I actually sort of don't want to study Nash equilibria very much in this class. Like in particular, one of the kinds of intractability that's known that sort of there are no decoupled dynamics like multiplicative weights or gradient descent that quickly converge to Nash equilibria in general games. Means that if these are the kinds of objects you like, the kinds of tools that we're developing in this class are not going to help you find them. And even worse, there might not be any tools to help you find these things. And so I want to think about a different class of equilibria that will be very closely related to the kinds of tools we're developing in this class. And as a result, are sort of computationally tractable and share many of the nice properties of Nash equilibria, but yeah, without the sort of computational hardness. So we're going to be able to talk about these things constructively, not just prove their existence, but actually give algorithms, and in fact, not just algorithms, but decoupled dynamics that players could use in a game without coordinating to find these things. Okay. And okay. So what's this alternative solution concept? They're called correlated equilibria. And how does a correlated equilibrium deviate from a Nash equilibrium? The high-level idea is sort of going to be very similar. You want it to be sort of you want a correlated equilibrium to represent some stable solution where nobody can benefit by unilaterally deviating from their part of the correlated equilibrium. But what's sort of the important aspect of a correlated equilibrium is that players are allowed to randomize their actions. Okay, well, in Nash equilibria, players could randomize their actions. Like these action sets could have represented sets of probability distributions. But in a Nash equilibrium, if the action sets corresponded to distributions, the joint distribution on all n actions would have been a product distribution. Everyone would have been randomizing independently of one another. The difference between a Nash equilibrium and a correlated equilibrium is that in a correlated equilibrium, players are somehow randomizing, potentially, using correlated randomness. Okay, now, what does that even mean in the real world? Like, how would we randomize with correlated randomness? Typically the way you would imagine this is that as part of implementing a correlated equilibrium, there would be a correlating device. And sort of the canonical example of a correlating device is like a traffic light. Okay, somehow like what we implement at intersections is a correlated equilibrium where if say we're at like a, T intersection or something. If I go, you stop. And if you go, I stop. Okay, we're playing actions that are correlated with one another. We are both getting benefit from this correlation. We're avoiding head-on collisions. And the reason we are able to implement this is because there is a device, a physical device, a traffic light, that is sending a signal to me and is sending a signal to you. I probably can't see your signal, right? I can't necessarily see the light that is facing in your direction, but I know how a traffic light works, and so I have confidence that conditional on seeing green, you are seeing red and vice versa. So I am seeing like part of a joint distribution, and I understand the correlation in this joint distribution, and so I can think to myself, given that I'm seeing a red light, would it be in my benefit to deviate and to like go? And I can think to myself, no, it wouldn't, because I think it's quite likely that the oncoming traffic has a green light and they're going to be going and they're going to smash into me if I do that. Okay, so that the general idea is that I'll see some signal, the light from the traffic light. At that point, I will think to myself, should I like continue and follow my part of the correlated equilibrium, or should I deviate? I get to deviate as a function of the signal I see. And a correlated distribution on actions will be a correlated equilibrium if the answer to that question after I see the signal is always I should not deviate. Okay, that's at a high level what a correlated equilibrium is. So how do we formalize that? Okay, so let's say that P is a distribution over action vectors. Okay, so every vector that lives in this space specifies an action for each one of the n players. And P is a distribution over those vectors. It's not a product distribution. It's just an arbitrary distribution over those vectors. So there can be correlation in this distribution. It can be that every time I see green, you see red. Every time I see go, one of my actions, you see stop. Okay. this distribution is an epsilon approximate correlated equilibrium if for all players I and for all deviation functions, which are just arbitrary mappings from my action set back to itself. Okay, these are functions that are sort of like little devils on my shoulder that are saying, you see a red light, why don't you go anyway? Right? It's sort of saying, that would be the mapping that said, when you're suggested to stop, you should go, right? These are little sort of devils on your shoulder that suggest to you that instead of doing what you're suggested as a function of that suggestion, you should do something else. Okay, and this distribution, it's a correlated equilibrium if simultaneously for every player and simultaneously for every little devil that might be sitting on their shoulder, telling them what they should do instead of what they were told to do as part of the correlated equilibrium. That if we look at the expected cost that they have when they follow their part of the suggestion, as does everyone else, when the suggestions are drawn from this correlated distribution, that this cost should be only smaller than the cost they would have counterfactually experienced if, again, in expectation over a draw of an action profile from this distribution, when I look at player I's cost, when player I, rather than faithfully following the suggestion, instead plays this action modification rule. Okay, instead of playing action AI, plays action phi of AI, right? Which might say, things like, when you're told to stop, go, and when you're told to go, stop. But nobody else deviates. Everybody else continues to play their part of the correlated equilibrium. That, like for every possible deviation, it shouldn't be beneficial to do this. And if it's an epsilon approximate correlated equilibrium, maybe you could get some epsilon benefit by deviating, but not more than that. Okay, so it's a correlated equilibrium if, just like a Nash equilibrium, a distribution is a correlated equilibrium if there's no beneficial deviation. But now, because of sort of there's some implicit sequencing of the game where first I show you your signal, you're part of the correlated equilibrium. Like you see a green light, I whisper in your ear, I think you should go. What are your deviations? Because of the sequencing, you're allowed to decide whether and what to deviate to after you see that signal. And so you have a much richer set of deviations. You can deviate not just to a fixed action, you can deviate to some policy that maps the thing you're recommended to do as part of the correlated equilibrium to something else, right? Like if there's k actions, there's like k to the k such policies. For every action you're recommended, you could play any of your k other actions. And something the correlated equilibrium, if all of those alternative policies mapping recommendations to actions would not help you. Okay, does this make sense? So I think you should sort of, so this is the definition. P is just some joint distribution, but I think it's helpful to think about this as something like a two-stage game, where in stage one, you get a recommendation, something like a green light or a red light, or more generally, an arbitrary action from your action space. And then after seeing that recommendation, that's when you decide what action to take. One thing you could do is play the action that was recommended to you, but you don't have to. You could do something else. You could deviate according to an arbitrary policy, mapping what you're recommended to what you should actually do. And it's a correlated equilibrium if it's a best response to just do what you were told and follow the instructions. Does that make sense? Okay. So this condition, this correlated equilibrium condition, it's very closely related to some notion of regret, but a richer, sort of more demanding notion of regret than we've seen so far, right? Like, you know, to sort of squint for a moment, like when we talked about regret, what kinds of expressions did we write down? Well, we said, okay, like, you know, on the left-hand side, you've got the cost for, you know, what you actually did. So usually it was like the sum over a bunch of rounds of the cost for what actually occurred. If you squint for a moment, maybe you can, you know, blur this expectation into a sum. Expectation is just a sum. Okay. And on the right-hand side, you had the cost you would have experienced in some counterfactual world where you, instead of doing what you did something else, something really simple, just played a fixed action every day, but everyone else did the same thing. But otherwise, the costs for the actions remained the same. Or if you're playing in a game, you know, what that would mean is everyone else continued doing what they were doing in this counterfactual world. You were the only one who deviated. Okay, so it's kind of like what we have here, right? Like, you know, here's what happens on the left if you don't deviate, like your actual realized cost for playing in the correlated equilibrium. On the right, you've got sort of, you know, your cost in some counterfactual world where everyone else continued doing what they were doing. And you deviated, but in a way that was more complicated than your deviations were allowed to be when we were talking about regret previously. Previously, your deviations were just to, you know, whatever you were doing before, like we considered deviations to things like always play rock, right? Just like fixed functions. We had no regret to the best action in hindsight. Whereas here, we're sort of comparing to sort of a more complicated set of deviations. These kinds of deviations are expressive enough to, you know, correspond to the best fixed action in hindsight. A very simple devil standing on your shoulder might just say, you know, just always go, no matter what the light is. But a more complicated one could say more complicated things. Okay, so this is like a, you know, we're going to write it down in a moment, but this is closely related to regret, but regret to a stronger benchmark class than we've been thinking about so far. Um, let's see. So let me try to parse your question. So if epsilon is 0, then by definition, P is a correlated equilibrium. So certainly it is a distribution over correlated equilibria actions. But there are correlated equilibria that are not Nash equilibria. So it is not the case that the only way you can set epsilon to be 0 is to randomize over Nash equilibria. And that's important because we're going to give algorithms for finding correlated equilibria, but as far as anyone knows, Nash equilibria are intractable to find. Good question. Okay, so let's try to, you know, like maybe using this definition as a model, define a more demanding notion of regret that's going to correspond to the kind of thing that we're asking for from a correlated equilibrium. Okay, it'll be a multi-objective notion of regret, rather than just asking that your cumulative cost overall is less than something. It's sort of going to allow us to, it's going to sort of, there's two ways you can think about it. You can sort of think about it as either specifying a multi-objective regret notion, or as just a regret notion to a much richer class of benchmarks. Okay. So let's fix an action space A for a learner. And a class phi of, let's call them action modification rules. Which are functions mapping the action space back to itself. Okay, so things like we've got here. So given a transcript pi t, so let's say a record of play of this learner against an adversary who's choosing a loss function at every round. So it's for every time step, what we have is an action chosen by the learner and a loss function chosen by the adversary. And this has gone on for t rounds. The learner's regret to a particular strategy modification rule, action modification rule, in this collection phi is, well, the sum over all of the time steps of the difference between the loss the learner actually experienced at round t, given how things transpired, minus the loss that the learner would have experienced if, rather than playing AT at round t, they played the thing that the strategy modification rule, the action modification rule suggests them when you plug in AT. Okay, so the action modification rule is sort of something that is a backseat driver. It says, in hindsight, every time you played action 5, you should have played action 7. Every time you played action 6, you should have played action 2. When you played action 7, that was good. Keep doing that. Okay, it's something that can go back and for each of your actions, suggest that you should have done something different as a function of that action. Okay, so this is a lot like sort of the kind of regret we talked about previously, except there, now in this language, we were limiting ourselves to a very simple kind of action modification rule that changed everything to, playing action 1. Right, like when we were talking about rock, paper, scissors, we were like, all right, let's make sure we're doing as well as playing rock every time. Let's make sure we're doing as well as playing paper every time. This is saying, okay, yeah, you have to do as well as playing rock every time or paper every time, because there are strategy modification rules potentially that always output rock or always output paper. But like also, you have to do as well as what would have happened in hindsight had every time you played paper, you played rock. Every time you played rock, you played scissors. Every time you played scissors, you kept doing that. Okay. And so then more generally, the learner has phi regret alpha if their maximum regret to any of the action modification rules in this class phi is bounded by alpha. Okay, and if phi is all action modification rules, We call this swap regret. Okay. Does this make sense? Yeah. Yes. So one thing. Okay, good. So let's reflect on swap regret for a moment, both how it generalizes the kind of regret we've been talking about already, and how it has this weird self-referential flavor that the simpler kind of regret that we were talking about doesn't have. Okay, so first of all, if you have no swap regret, you also have no regret of the sort we've been talking about so far. Because what is, and now we shouldn't just call that regret anymore. Let's give it a name. In the literature, for reasons that Ricky Bora knows, that kind of regret is called external regret. Okay, and sometimes this kind of regret is called internal regret. Yeah, these are, you can ask Ricky. External regret, which is just the kind of regret we've been talking about in this class so far, corresponds to the set of, corresponds to phi regret for the set of strategy modification rules phi that correspond to all constant functions. Things that ignore their input and always recommend rock, or always recommend scissors, or always recommend paper. Okay? If you have no phi regret with respect to constant functions, well, for every fixed action, there's a constant function that always recommends that action. That just means you're doing as well as the best fixed action in hindsight. Okay? Now, swap regret demands no regret with respect to all action modification rules, which sort of means, okay, you have to have no regret to the best fixed action, but also no regret to, there's a lot of these, right? Like if you have k actions, let's say, there's like on the order of k to the k action modification rules. For every input action, of which there are k, it can specify an arbitrary output action, of which there are k. So it's asking for something much stronger. No regret to this set of k to the k action modification rules simultaneously. Okay, so it's a multi-objective optimization problem, if you like, right? Saying, your regret to each of these strategy modification rules has to be small. Okay, so it's more general, it's stronger, but right, like what's weird about it, getting to sort of Natalie's question, this isn't saying that you have no regret to arbitrary policies or, and you have to think about like what is possible and what is not possible, right? Like you can't have no regret to like arbitrary sequences of actions because, say we're playing a coin flipping game where every day I flip a coin and you have to guess heads or tails. Well, in hindsight, of course, there is some sequence of actions that does great. The sequence of actions that corresponds to you getting the answer right every single day. But, it's clearly impossible to come up with an algorithm that'll guess the outcome of a coin flip correctly, more than half the time. And so we clearly can't have no regret to arbitrary sequences of actions or sequences of actions that are allowed to depend on the actual realization of the adversary's loss. So phi regret, it's a rich set of benchmarks, but the benchmarks are functions of the actions you chose as the learner. Right? The strategy modification rule in the counterfactual is applied to the sequence of actions that you chose. And so how rich this benchmark class is depends on what you did, right? Like if your algorithm, like if the way I played rock, paper, scissors was by just playing rock every day or playing any constant function, then the set of strategy modification rules actually wouldn't form a very rich benchmark class because there's a lot of strategy modification rules, but like they're all constants if the input is constant, right? Like if so one thing we might want to be careful of as we're sort of deriving algorithms to get no phi regret is that we're not doing it maybe in sort of stupid ways by restricting intentionally restricting the complexity of the benchmark class by applying only simple strategies. Like maybe like we won't be, but you should like worry about that maybe. Okay, but does that make sense? Like somehow like one weirdness about this definition. I mean, it's it corresponds very closely to correlated equilibrium, by the way. So like, it's a very well motivated definition. But one weirdness about this definition is that it is the benchmark class is self-referential. It depends on the actions you played. And so how strong these sort of counterfactual sequences are that apply strategy modification rules to what you did depends on what you did. Maybe like one other observation that'll just sort of bound what is possible. Suppose you played a different action every single day. Okay? Then there is a strategy modification rule that maps your sequence of play to an arbitrary sequence of outcomes. Right? Because it can map every action to something, like the only restriction here is that it has to map the same action to the same thing. So every time you played action 5, it has to tell you the same thing. But if you played this for t rounds and you had t different actions, and you played action 1, then 2, then 3, then 4, a strategy modification rule would just be specifying an arbitrary strategy that you'd have to play at every day, an arbitrary action that you could play at every day, right? So it could specify the best, it could demand that you compete with the pointwise best action in hindsight every day that you could have come up with only had you known the outcome of the coin flip or the realization of the adversary's cost vector. And so if you think about that, it's clearly impossible to compete with that. And so when we derive bounds that are going to give us no swap regret, they're not going to they're going to have to be because this kind of regret is qualitatively so much stronger. The bounds are going to have to be correspondingly quantitatively weaker. When we derived bounds for the multiplicative weights algorithm, we depended only logarithmically on the number of actions, which means we could have played a t action game for t rounds and gotten a non-trivial regret bound. But because of this observation that swap regret would require that you guess a coin flip correctly every single day if you played a different action every single day, it means that we can't possibly get bounds that are going to allow us to play games that have an action space that is as long as the number of rounds we're going to play for. We're to get non-trivial regret bounds for swap regret, we'll have to play at the very least for a number of rounds that is sort of larger than the number of actions we have available, which is qualitatively different than what we could get for external regret. Multiplicative weights depended only logarithmically on the number of actions we had. So actually we could get no external regret even when the number of actions we had was exponentially larger than the time horizon. It's going to be sort of qualitatively different for swap regret for exactly this reason. Okay, good. Yeah.
You just have a finding when someone shows you the statistical average or rate of the optimizer action kind of time, you could really get no effect and no out because it's possible action. You can get better payoff by focusing on different parts of the system, potentially
Yeah, it's a
it may not be yeah, but if the case that the first half is going to be a particular pattern of loss, the second half is going to be a particular pattern of loss. ideally you should do that.
That's right. Yeah, it's a weird definition, but a good one, despite the fact that it's weird. Like, and so, okay. First, it corresponds, and historically is closely related to correlated equilibrium. But also, as we start talking about calibration, it's going to have very close connections to calibration as well. So like, I agree with you, it's a weird self-referential definition, but it's not weird for like arbitrary reasons. Like, it's getting at something important, I think.
Then ask for the profit that a bunch together from
Yeah, I think that's a question that probably makes little sense to most of the people in the room, but the answer is yes. Yes, that's right. So like when we talk about calibration, we're gonna, in order to get non-trivial bounds, have to like, bunch together. You can't have an action set that corresponds to like all real numbers. You're gonna have to like bunch them together in some way that is related to the time horizon. Okay. All good questions. So, okay, the last thing I want to do today is sort of just formally make the connection between this notion of swap regret and this notion of correlated equilibrium. So if you sort of remember, or we've talked in this class a little bit about sort of learning dynamics, not so much for their own sake, but really as a tool. Like when we proved the minimax theorem, like how did we prove the minimax theorem? We imagined that there were two players in this zero-sum game who were repeatedly in a sequence of T rounds playing against one another. One of them was using a no-regret learning algorithm. The other was doing something else, maybe also using a no-regret learning algorithm, maybe a value oracle. And we thought about their cumulative payoff that would result if they were playing this game against one another. Okay, now, in the same way, we can imagine in an n-player game, a general sum game, players repeatedly playing against one another using learning algorithms. Maybe it's, like maybe they're really doing this even, right? Like maybe it's not like a thought experiment just in service of proving some theorem, but like maybe they're really doing it. Like maybe there's an ad auction every day and people are, bidding in it, and maybe they're bidding in it using like clever learning algorithms. And so you can ask, suppose the learning algorithms they're using are sufficiently clever to guarantee not just no external regret, like they're not just using multiplicative weights, but maybe they're playing learning algorithms that are sufficiently clever to guarantee the stronger thing, no swap regret. Okay, and we'll derive in the coming lectures algorithms that are sufficiently clever to do that. What could we say about their empirical, what could we say about their empirical history of play? Like what actually happens when the players don't necessarily talk to one another, right? They're just independently running these learning algorithms that happen to independently have these like swap regret guarantees. Well, the answer is going to be that their empirical history of play converges to a correlated equilibrium. Okay, so this is something that we can think of both as just, maybe a descriptive statement about the world. Like maybe we imagine that in large online interactions, things like ad auctions say, people really are going to be using learning algorithms to interact with each other repeatedly. In which case, this kind of theorem is going to say, correlated equilibria, maybe unlike Nash equilibria, are like a computationally plausible solution concept. It's not just something that like exists, whose existence we proved with a fixed point theorem, and were we to get there, somehow we would stay there. Like, no, we have like a concrete story about how and why and how and why you would get there and how long it would take. If everyone plays according to these hopefully natural learning algorithms, like that's where you inevitably end up. Okay, and as a descriptive statement of the world, this is good motivation for studying things like, what are the properties of correlated equilibria in the market you've set up? Are they, if you're going to inevitably get there, maybe you want to design the market so that the property, so that good things happen in correlated equilibria. Alternately, you can think of this kind of statement as an algorithm. Like a correlated equilibrium is an object that I might want to get my hands on. Maybe I'm designing, Waze 3.0, some traffic routing app, but like I want to, I aspire to like take over the world. Basically, everyone's going to be using Waze 3.0, and so I don't want to just sort of like greedily tell people their best responses. I want to do like traffic engineering. I want to coordinate where everyone is going so as to minimize traffic congestion. But like, I'm wary that some competitor might come along, and if I'm telling people things that are bad ideas, conditional on what I tell them, then they might open up this competitor app and follow those instructions instead. And so I won't be able to take over the world unless I'm telling people things that are actually a good idea for them to follow. But I'm allowed to use, like, to the extent that I can take over the world and everything's going through my servers, I don't have to give people independent instructions. I can coordinate the instructions, right? So in that case, I might want to do something like compute the traffic minimizing correlated equilibrium. And so you might start asking yourself, well, how do I even compute a correlated equilibrium? And to the extent that we have efficient learning algorithms that, when played against each other, converge to correlated equilibria, that gives us a concrete algorithm to compute a correlated equilibrium. Just like run these learning algorithms for a sufficiently long time until we get convergence. Okay, so maybe sort of two motivations for this. All right, so let's fix a game and a sequence of action profiles a 1 through a t. Okay, each action profile is a vector of length n. It's specifying what all n players did. Okay, so one way we could come up with a sequence of action profiles is we could assign an algorithm to each player that tells them as a function of what's happened previously, like what action should they pick today. Okay, if everyone has a learning algorithm telling them as a function of what's happened in the past, what action should they pick today, and we just run these learning algorithms for all n players for t rounds, we will have produced a sequence of action profiles. We'll say that this sequence has swap regret alpha if for every player I, if we look at the strategy modification rule for that player, that causes them to have maximum regret given what their opponents did. Okay, so what do I mean by regret here? Because now, it's not an adversary choosing loss functions, it's a bunch of opponents choosing actions. Well, the loss that I'm going to use to measure regret is the cost function for action I in this game, given what his opponents did. So his regret, given a strategy modification rule, is just the difference between the cost that he actually experienced in this sequence and the cost that he would have experienced had, instead of playing action AIT at round T, he instead applied his strategy modification rule and played action phi of AIT. But everyone else continued doing what they were already doing. If simultaneously for every strategy modification rule and simultaneously for every player, they have regret at most alpha to that strategy modification rule, then we'll say that this sequence of play profiles has regret at most alpha. Okay. So again, how would we generate such a thing? Well, if we had in our hands an algorithm for the, online sequential decision-making problem, something like multiplicative weights or online gradient descent, that promised that in the worst case over choices of costs by an adversary, not just the external regret, but the swap regret was something that tended to 0, then just by running a copy of that algorithm for every player, we would be guaranteed to generate a sequence of action profiles that had regret, swap regret tending to 0, because we can just think of the choices of actions by the other players as being one instantiation of what an adversary might do, right? Like, this is where we're going to get some of the power in sort of giving regret bounds that hold not against distributions, but against adversaries, right? Like, there's no distribution here. Like, the other actions are being chosen in some complicated way, right? Not an arbitrary way, like, right? Like maybe, maybe once we pin down this algorithm, we'll know something about how they're being chosen, but in a complicated way, a non-distributional way. And one easy way to get a statement like this is if we have learning algorithms that independently for every player guarantee that their swap regret tends to 0, no matter what sequence of costs they're faced with. Okay, then, right, the sort of, this is where, this is maybe indicative of why adversarial bounds are nice. It's not that, like, in any particular scenario, we're really playing against, a maximally adversarial bad guy. We're not really solving a min-max optimization problem. It's that the environment we're playing against is complicated. We don't understand it in great detail. If we have an adversarial bound, we don't need to understand it. Okay, so if we had algorithms that guaranteed against adversaries that the swap regret tended to 0, we would have in our hands a way to generate sequences of action profiles that satisfied the swap regret guarantee by just having each player independently play a copy of this algorithm. So let's fix a game. And an action profile sequence A1 through AT that has swap regret alpha. And then let's let the distribution P be the uniform distribution over this set of action profiles. Okay, so we, have this list of action profiles that maybe we got by having players play against one another with algorithms that guarantee them no swap regret. It's not a distribution, it's like it's a sequence, But the distribution I'm going to define over this is going to be the distribution that selects a time step uniformly at random and then pulls out of its hat that action profile, the uniform distribution over these action profiles. Okay, that is a distribution in which the actions are correlated with one another through time, because I'm selecting the same time step for every action. Okay, this defines some correlated distribution over actions, right? This is where we're using the fact that correlated equilibria, but not Nash equilibria, are allowed to be defined as non-product distributions. Okay, this construction doesn't produce a Nash equilibrium just because it's not of the same type as a Nash equilibrium. These are not independent distributions over players. Okay. Then P is an epsilon approximate correlated equilibrium for epsilon equals alpha over T. Okay. So alpha, the way we defined it, is not normalized. It's not dividing by T. So alpha, you should think of something as, bigger than 1, but hopefully growing sublinearly, something like root T. And so, if alpha, for example, was growing with root T, then epsilon would be something like 1 over root T. Yeah. That's right. That's right. Yeah. So if you think about, for example, a game in which there's, every player has a finite number of actions, and what they play every day is a distribution over those actions. Yeah. Then, each of, fixing a particular time step, every player would be playing according to some distribution, but they wouldn't be correlated within each time step, right? But P, how do I select an action from P? First, I select a time step uniformly at random, like time step 17, and then I sample from each of the players' product distributions, the ones they played at time step 17. And because it's 17 for all of the players, they're correlated. They're correlated through the selection of time. Yeah.
That A function equals A P, and in the fact they two left together. So the uniform distribution is not typically time step. Is it?
Yes. Yeah. Sure. Yeah. It could be that there's some multiplicity here. The same action profile could be repeated. Like if we're playing rock, paper, scissors, there's just not that many distinct action profiles. So, they will show up different numbers of times, and this will correspond, playing uniformly over these will have some other representation where I specify a weight for each of the possible action profiles. But no matter what it is, the distribution I'm talking about is always uniform over this set. But you're right that it could be that A1 is equal to A23. That's right. It's a uniform distribution over, you take these T vectors, you put them in a hat, you shake the hat up, you pull one out. Okay, the statement clear? Okay. So, the definition of swap regret is close enough to the definition of a correlated equilibrium that this is going to follow basically just from unrolling the definitions. But let's do it. So first of all, what do we need to show? We need to show that for every player I, and for every action modification rule, that if we go back in hindsight, with the benefit of hindsight, and apply that action modification rule to every action they played at each time step T, that the resulting counterfactual transcript would not have been one that yielded them substantially lower cost. Okay, so we need to show this for all players and all action modification rules. Let's fix a particular player and a particular action modification rule. All right, so on the left-hand side, we've got the cost that they would experience if they just politely follow their part of this purported correlated equilibrium and do not try to deviate. Now we know something about this distribution. It's not an arbitrary distribution. We constructed it. So what is this expected cost? Well, the distribution is just uniform over these t action vectors. So the expected cost in this case is just, well, the sum over all of the action vectors of the cost of that action vector times the probability of playing. Well, it's uniform. So the probability of playing each one is 1 over t. So it's just the average cost that they experience over the t action vector. This is just what an expectation is when the expectation is being taken over a uniform distribution over t things. And, now we've got a sum over these t things. And what do we know? Well, we know that this sequence of action profiles has small swap regret for every player. So by definition, this means that if we look at the sum over all of the time steps of the cost that player I would have experienced had, rather than playing AT, AIT, they're part of the correlated equilibrium, they instead counterfactually played what their strategy modification rule would have suggested they should play. And everyone else continued playing in the same way. Then up to an alpha term, this would have been only more costly for them. This is just invoking the assumption that the sequence has swap regret alpha, and so in particular, the regret that any player I has to any particular strategy modification rule, phi I is alpha. But, that was basically it. Just writing things again as a expectation over this uniform distribution. What this gives us is that again, writing things in expectation over a draw from this distribution that we're trying to show as a correlated equilibrium. If after you see your signal, after you see the traffic light, but nothing else, you instead of playing what you were told to play, you play the thing that your strategy modification rule is really trying to get you to play instead, but nobody else deviates. Then your expected cost will go down by at most alpha over t. So it's an alpha over t approximate correlated equilibrium. Okay. So what you can see from this is like basically, in some sense, like nothing has happened in this lecture. Like we defined a notion of regret that was tailored to be the same thing that we used to define correlated equilibrium. So like, of course, this is true. But the upshot is that we've got this particular notion of regret now, phi regret, and more generally, or less generally, but more powerfully, swap regret. And we can sort of put all of this into practice. We can generate a sequence, we can efficiently generate a sequence of action profiles that have diminishing swap regret, and therefore get convergence to and get computation of a correlated equilibrium if we can derive algorithms that guarantee that, in particular, against an adversary, they have no swap regret.
Like, I'm like happen to do pretty close. So like, tell me if like this is like the correct way to understand that. Because with an epsilon, like ideally like this, right? But in fact, this implies that the players have almost all the time do that spot, right? Not just that they're playing music that they're close, but like you have to, if they were playing the other music, like that gap is just more.
Let's see. So like it's not necessarily the case that like it, let me try to parse your question. Because like it's not the case that a correlated equilibria is a distribution over Nash equilibria. So it's not the case that at every step players are playing anything close to a best response to what the others are doing at that step. Conditioned on the signal. Yeah, that's right. So this is, if you have a very, like, so the way this is parametrized, if you have an epsilon approximate correlated equilibrium for a very tiny value epsilon, then for every signal, the following thing must be small. The frequency of that signal times the benefit you would get by deviating when you have that signal. So either the benefit you get from deviating when you see that signal is very small, which means, or the signal hardly ever occurs. It might be that like, you've spent your whole life driving, around New Jersey and Philadelphia, you're really good at driving. And then all of a sudden you see like, tomorrow, like a purple light and you don't know what to do and you mess it up, but you never see a purple light again. You could still converge to like an approximate correlated equilibrium, not that you have like low regret, like conditional on seeing purple lights, just that like they don't come up that often.
I'll actually take time to do that, right? Maybe just have fun. Now the other player is totally different type of thing. So like in this scenario, because my actual mapping of signals to action, like really involved the distribution on mapping code, like it was all like the actual correlated behavior not map, right? Then if I deviated to like something like that was actually that, that's not the exact level.
Yeah, not sure I totally get it, but it sounds smart. Yeah, let's talk about it later. All right, thanks guys.